Hi everyone. This week's lesson is all about applying the slope-intercept form to the real world. So we're going to be looking at applications of the slope-intercept form. So before we jump into the lesson, I wanted to actually just spend a couple minutes reviewing slope-intercept form. So I'm just going to bring you guys up to this little diagram that I've drawn here, okay? So we already know, right, that the general form of a line is written in this form. And we call this form slope-intercept form because it contains the slope and it also contains our y-intercept. So that's how it gets its name, slope-intercept form, okay? And we know that we already know all this stuff, right? We know that the slope of the line is referring to how much the line is increasing or changing, how much it's going up every time it moves over. So our slope kind of tells us how steep the line is. Remember, slope is rise over run. And we also remember, don't forget, there's also the slope formula that we use, right? So that should be in your tool belt too, right? We know how to calculate slope if we're given 2 points, okay? We also learned about this y-intercept, right? This b value. So remembering that our y-intercept, when we talk about our y-intercept, we're talking about when our line crosses the vertical axes, right? Our y-intercept, okay? So now, before we make the transition to real world problems, I just want us to kind of look at the different quadrants, okay? Refresh your memory of the quadrants. This is, when we're talking about a grid space, this area is quadrant 1, this is quadrant 2, this is quadrant 3, and this is quadrant 4, okay? This is from our very first lesson on the coordinate space, okay? So when we talk about real world problems, a lot of the time we are only in quadrant 1. We are only within quadrant 1. And the reason is because in the real world, in the real world, we usually only deal with positive numbers, right? Positive numbers of x, positive numbers of y. So when we talk about real world problems, sometimes we would only draw a graph that includes just quadrant 1, right? Where we have positive values and positive values. So it's like we're only taking a screenshot of this part of the graph, right? That little top corner. Okay. So again, like I said, in real world problems, sometimes we only work within quadrant 1. Okay. So before we get started, I want to talk about a few things. So we've already discussed what dependent and independent variables are, okay? And I'm going to go over a couple examples. This is not a complete list, but this is some examples of what you may come across. So dependent variables, remember, those depend on something else. So those could be things like cost, price, distance, and then independent variables, those are things that don't depend on anything. So time, right? The number of hours, the number of items, the number of events, okay? And hopefully this will make more sense as we do some actual problems, okay? But if we look at all these items, right? Cost, price, distance, we would never have a negative cost, right? Or a negative price or a negative distance, right? And similarly, we would never have a negative amount of time or a negative number of items, right? So it does make sense that we are only working in quadrant 1, okay? So I have this brief little graph here, and I just decided to make my dependent variable, I decided to make it the amount of money, okay? So maybe this is the amount of money in my paycheck, and my independent is the number of hours I work, okay? So we can see that if I work 6 hours, at whatever job I have, that means that I am going to make approximately $30, right? Because this point right here would be 6 comma 30, okay? Similarly, if I work, let's say that lines up with 11 and this lines up with 45, I know it's not perfect, but when I work 11 hours, I would make $45 or something like that, right? So you would get your rate of change from the graph, okay? I also want to talk about what our y-intercept means in this case, right? So remember, our y-intercept is when we cross our vertical axes, So in real life problems, we turn the word slope into rate of change. So when we talk about real world problems, and I keep saying that over and over again, sorry about that, but we call this point the initial value. It's called the initial value or the starting value or the starting amount, okay? So when we talk about a graph, it's a y-intercept. When we talk about the real world, it's an initial value. It's the starting amount, okay? And let me explain why we call it the initial value, okay? So that point right there, that point is 0, 15, okay? So what that means is if I work 0 hours, right, I still get paid $15. Right? So maybe this job, I get $15 just for showing up on time, and then I get a certain amount per hour after that, right? So we say that my initial value is $15. My initial value is $15. So my y-intercept occurs at 0, 15, but I spelled that wrong, sorry, intercept. Oh, sorry. Intercept. Okay, it's the point 0, 15. Or we say the initial value is $15. Okay, $15. So the initial value includes units, just like the rate of change includes units. Okay, so when we hear the word initial value, I want you to relate it to the y-intercept. Okay, so that took a bit of time, I know, but now let's go back to the actual lesson part and let's work through the problem so we can see what we're actually dealing with here. Okay, so I'm going to briefly go over, we already went over this, but let's go over it again, okay? Rate of change, we know, is represented by our m, right, in our slope-intercept form. Our initial value, right, that is b, that's our y-intercept. Our independent, okay, and you guys got to get this sorted. Independent is our x, and dependent is our y, okay? Your equation will always be written with your dependent variable as the subject of the equation, right? So meaning y is always isolated. So your dependent variable will always be isolated. Okay. Let's read question 1 and see how we do with it, okay? A computer repair shop charges a $25 fee in addition to $40 per hour to service a computer. Write an equation to represent the total cost to service a computer and identify your variables. Okay, In my opinion, the order of these questions is kind of off. I'm gonna get us to start by figuring out what our variables are. So what is our independent and what is our dependent variables? Okay. The easiest thing to identify is the dependent variable. And I'll tell you why. The question tells you, okay? The question says, write an equation to represent the total cost, right? So we want an equation that represents total cost. This makes total cost our dependent variable, right? That is going to be the subject of our equation, right? The subject. So total cost is going to be isolated on one side of our equation. Okay. And then now our independent variable. So what is something that influences cost? Okay. Well, I can see that I have two parts to my price. I have $25 fee and I have $40 per hour. Okay. So my $25 fee, that's fixed. Okay. No matter what, I have to pay that fee. But because of this $40 per hour, my total cost could go up depending on the number of hours, right? So the independent variable has to be number of hours, okay? Because hours are what will cause price to go up, right? More hours, higher cost. Okay, so now that we have those two, let's identify the rate of change. So remember, rate of change is change in our dependent variable over the change in our independent variable. So how much, I'll just write this, how much does cost change per one of your hours? So per independent variable, per 1 hour, right? That's the question you have to ask to find the rate of change. Okay, well, it's pretty clear that it says the price will increase for every $40. So that means our rate of change, and remember, rate of change has units. Our rate of change is $40 per hour. An hour we can represent with just an H, okay? Or if you prefer, you can write out the word hour. Okay, so there is our rate of change, and we've included units, because if we don't include units, we're not correct. All right, so the initial fee. So when we talk about initial fee, I want you to ask yourself this. What is cost if number of hours is 0, right? 0, our initial starting. So even if our computer is takes 1 second for them to fix, right? We still have to pay that $25 fee, okay? And initial value has units, but it doesn't have 2 units. Initial value is only 1 unit. So the initial value is $25, okay? So rate always has 2 units, right? Dollars per hour. Initial value is just, 1 unit, okay? So now that we've done that, let's combine all of these items and finally create our equation. Before I do that, I'm going to define my variables, okay? So I'm going to let x equal, now remember, x is our independent variable. So x is going to be the number of hours that our repair job takes, number of hours. And then, of course, our y is going to represent the total cost. Total cost. Okay. Now, I didn't have to use x and y. I could have used C for cost and t for time, you know, it doesn't matter, but I'm going to stick to x and y for now. So let's just write out slope-intercept form so we have it. Y equals m times x plus b. Okay, so for us, our equation is going to be y equals m. So m, when we put it into our equation, we don't need to put the units. So what we're going to do is we're just going to put that 40 in. So in an equation, we don't put units. So 40 times x plus our initial value. So plus $25. Okay? So this is my equation. This is my final equation in slope-intercept form. Okay? And now I could actually write a word equation. I could say that total cost is equal to, and now I am going to use units, so $40 per hour. And remember, what is our x? X is the number of hours plus $25. Okay? So that makes sense, right? This is our word equation. So we would multiply the number of hours by $40 and then add $25 to the total to get the total cost. Okay, so that's question 1, and we took our time going through it because this is a tricky part, okay? Students tend to struggle with these word problems. So let's move on to question 2. An online photo printing shop, okay, so you send photos to go get printed off. It charges 15 cents per print, okay, plus an additional $2.95 shipping charge, okay? So let's say you have 100 pictures. Each picture is going to cost 15 cents to print, and then on top of that, you have to pay a $2.95 shipping charge, okay? And we're going to write an equation to model the total cost for printing the pictures. And we're also going to identify our variables like we did before. So again, I want to start with the variables. And the easiest is our dependent variable because it tells us in the problem, right? What do we want to make an equation about? Well, we want to make an equation that models, again, total cost. So that means our dependent variable is total cost again. It won't always be total cost, but total cost. Okay. Now, let's figure out what variable would impact the total cost. So what would affect my cost? So let's read the question one more time. An online photo printing shop charges 15 cents per print in addition to a $2.95 shipping charge. Okay, so what I should be able to recognize is that this $2.95, it's constant, okay? It doesn't matter how many photos I print off. I'm still going to have to pay, the $2.95, okay? So that doesn't increase. But what would increase my price is, well, if we look at this, 15 cents per print. So if the number of pictures I want printed is higher, my price will be higher. If the number of prints I want is lower, my price will be lower. So my independent variable is going to be the number of prints, right? Prints or photos. Okay, so what is the rate of change? So again, how much does cost increase? How much does cost increase every time we add one more print? Well, we already know that, right? It's in the problem. The rate of change is 15 cents per print, right? So every time we add one more picture, one more print, Price goes up by 15 cents. Okay. What is the initial value? Okay. So let's pretend for some reason I ordered 0 prints. I don't know why, but I ordered 0 prints. What would I still have to pay? Well, I still have to pay the shipping charge, right? To ship what? I don't know, but you know what I mean. The shipping charge is still there. So my initial value, regardless of the number of prints, is going to be $2.95. All right. So let's combine all of our stuff together here. So again, we're going to let X, which is our independent variable, represent the number of prints or the number of photos. And we're going to let Y represent the total cost. Total cost. Okay. So again, remember, Y equals mx plus b. So we're using what we've already figured out, and we're creating an equation. So Y equals, and remember, don't include units when you write the equation. So Y equals 0.15 times X plus 295. And there we go. That's my final answer. Okay. I can write a word equation, right? Total cost equals 15 cents per print. That's my rate of change. Times the number of prints. That's my X. Plus my shipping charge, which is $2.95. Okay. There we go. That's question 2. Question 3. Mark bought a season ticket to the ski resort for $395. However, he must pay $25 to rent skis each time he goes skiing. Write an equation to model the total costs that Mark will pay for skiing this season. Okay, so again, we're writing an equation that has to do with total cost. Okay, so yes, we're dealing with a lot of total costs. It's not always about cost, but you can see that price and cost comes up a lot. So again, this makes our life kind of easy, but the dependent variable is again total cost, because that's what we want to make our equation represent, right? That we want that to be our Y, our isolated variable. Okay, again, now for our independent variable, we have to figure out what would increase or what would affect the cost. Okay, so let's read through the question again. So he bought a season ticket to the ski resort for $395. Okay, he paid that. He's not getting that money back. Okay. In addition, however, he must pay $25 to rent skis each time he goes skiing. Okay. So what will affect the number of, what will affect the total cost, right? Well, isn't it the number of times he goes skiing? Because this doesn't change, right? That's it. But $25 happens each time he goes skiing. So if he goes skiing a lot, his price will be higher. If he doesn't go skiing a lot, his price will be lower. Okay? So the independent variable is the number of times he goes skiing. Or actually, I'm going to reword that. I'm going to write, just to make it easier, number of ski trips or something like that. Number of ski trips. Okay. So what is the rate of change? So how much does cost increase every time we add one more ski trip? Okay. Well, we know every time he adds one more ski trip, he has to pay that $25. So the rate of change is $25 per ski trip, per one ski trip, right? Okay, the initial value. Let's say right after Mark bought this season ticket, he breaks his legs and he ends up going skiing 0 times. Well, even if he goes skiing 0 times, he still paid that initial fee. So our initial value is $395. Remember, initial value has units, just like rate of change. Okay, so let's finish this up. So let X represent the number of ski trips. We're going to let Y represent the total cost again. Okay, and we're going to create our slope-intercept form equation. So Y is equal to 25 times X plus 395, right? And that's my final equation, right? So total cost, in other words, total cost equals $25 per, I'm going to be lazy and just write per ski. I'm lazy. And then I'm going to write per times the number of ski trips plus 395. Okay. Question 4. Jane bought a car with 23,000 miles on it. She determined that she typically drives 12,000 miles per year. Write an equation to show the number of miles on Jane's car after each year she drives it. Okay, this is a little bit different, right? So let's find our dependent variable. And our question will tell us what that is. It wants us to write an equation, right, to show the number of miles on Jane's car. So that is our dependent variable, okay? Number of miles, okay? Now, what would affect the number of miles, okay? So, we know that she bought a car, a used car, obviously, because the car already had 23,000 miles on it. And we know that, so that doesn't change, right? That's already there. That's going to be our initial value, hint, hint. And she determined that she typically drives 12,000 miles per year. Okay, keyword. Oh, sorry. The key thing you should be noticing is 12,000 miles per year. That per is really important. Okay, what does that tell you? It tells us that the number of years would affect the number of miles on her car. Okay, so number of years. Okay, so rate of change, right? We just talked about that. Okay, so the rate of change is how many miles does the car increase by every year? Well, we already know it's 12,000 miles per year. Okay, that slash, you need that slash. The initial value, so this is how many miles the car had when Jane owned the car for 0 years. So this is when she first bought the car, how many miles were on it? Well, we're told, right? It started off with 23,000 miles. All right, so let's put it all together. So we're going to let X represent the number of years. We're going to let Y represent the number of miles on her car. Miles. Okay. So Y is equal to 12,000 times X plus 23,000. Okay? So the number of miles equals, equals 12,000 miles per year times the number of years plus 23,000 miles. Right? So the number of miles in total will be 12,000 miles per year times the number of years plus the initial value, which is 23,000 miles.